Hello everybody, this is Fabricademy 2019, week number 6, Biofabricating Materials with Cecilia Raspanti, and go ahead, yeah.
Thank you. I will start with the screen sharing. Okay, can you see everything perfectly and hear me? Yes, great. Wonderful. So today we're going to be talking about biofabricating materials, where 2 weeks ago we actually looked at the coloring side and how we can create the pigments and chromes, dyes and inks from biomaterials. This week we work on really materializing all of these and still building upon those, so using them as building blocks for coloring our own materials. So we will look really at the context and how to grow and craft different materials. So just as an introduction, it's also important to look at what are biomaterials. So we will have a whole contextualization of what are these materials, what makes them biomaterials, what defines them, how do we categorize them, and then a very big overview of amazing people that have done research, starting from heritage techniques, mixing them with new technologies, new possibilities in digital fabrication or biotech, to create this beautiful, inspiring overview, which I hope you will enjoy. So when we talk about biomaterials, very often people actually confuse bio-based with biodegradable and biocompostable. So this year I thought it was really important to actually start also with this definition, because when a material is bio-based, it doesn't necessarily is also biodegradable or biocompostable. And very often when a material is bio-based and biodegradable, it's not biocompostable. So what does this mean? Bio-based materials are all of those materials where the focus is actually on what are they made of. And those are organic and inorganic materials. So what is the raw material that we're using? Is it biological? Yes. But biodegradable actually are all of those materials that are possibly broken down by microbes under very specific conditions. And these are set conditions that we create. While biocompostable takes this a whole other level, because this is mostly what we think with biodegradable, but biocompostable means that it's a complete microbial breakdown and assimilation into compost. So we're composting within 180 days or in less time than that. But when it's longer, we work again towards biodegradable. So these are sort of like building blocks to understand what we categorize as biomaterials. All of these materials can actually be categorized in 100 different ways. For example, in Amsterdam, we very often work between difference in crafted and grown materials, which is also a little bit how we're going to approach this lecture. Other people categorize them by what are they used for. So are they imitating plastics or bricks or yarns, or are they much more towards leather? And this distinction actually happens not because they're real leathers or because they're real plastics. They act or perform in a similar way, and society somehow needs also a way to relate to these materials. So when we talk about, for example, microbial leather, it isn't real leather, of course, but somehow the properties of these materials imitate the ones of regular leather. So it's a way for us to actually communicate about our work, the research we're doing, and trying to explain what are the alternatives that we are proposing. Keeping in mind that all of these are possible alternatives of which we still need to also understand what are the possible future complications. But also we can categorize them under raw ingredients and materials. And both of these are extremely important when you're building up your own material archive or when you start a taxonomy to understand better what your materials are and how do they function. You really need to understand the building blocks, so the raw materials, how these can combine, what are the properties of these, and how then they become made materials, which can be crafted or grown again. So we will start actually looking at two main categories, which are bioplastics of all different types, and then let's say bioleathers, or alternatives to leathers and alternatives to plastics. Why plastics? In general, I think that actually plastics are a fantastic material for certain aspects. In fact, not everything about plastics is bad. It's a material that lasts for a very long time. So it's perfect actually when we design something that needs to last for a very long time. It is though ridiculous when we use it to build something that needs to last, I don't know, 45 minutes, like a plastic cup at a party. There is no reason to work with plastics in that sense. So this whole lecture actually focuses also on trying to design your material together with the design of your product and actually create material that follows its functionality afterwards and not just taking a material because it's so easily usable or moldable, such as plastic, for whatever we want to design. This is actually a quote that I really enjoy, which is, "Plastic is a substance the earth cannot digest." And this comes from the Plastic Pollution Coalition. So this is mostly a little reference for you of what are plastics and where do they come from, to sort of also contextualize a little bit the fact that they come from nature. And of course, they're synthetic because they undergo synthetic processes, but they are all bio-based. And we're really working with bio-based polymers, even when we talk about plastics, most plastics at least. This is a small overview from Plastic Pollution Coalition, where they list very clearly 8 issues of plastics. The first one being that it never goes away, as I was mentioning earlier, because it takes forever to break down, but also that it spoils very much our underground waters. So actually by slowly breaking down, it pollutes our waters. It threatens wildlife. I think everybody has seen these horrible pictures with wildlife trapped into plastics. It poisons food chains in many different ways because they're eating our microplastics, affecting human health. They also attract many pollutants of different types, and actually they become conglomerates, and also they pile up in the environments. I think everybody has seen all these horrible piles of plastics, both at beaches but also simply at dumpsters. And unfortunately, they cost us billions to abate. So we're doing something somewhere extremely wrong in the way we use this material. But I don't want all of a sudden everybody to say, no more plastic for anything, because I do not fully agree on that. I think that whatever the material is, if we use it correctly, it actually has great potential. But the moment it's used and produced wrongly, we end up in problems such as these 8 issues. And for whoever is interested, actually, I will suggest to have a peek at the Plastic Pollution Coalition website, because they have extensive resources, a lot of knowledge is collected in there, and you will find quite some interesting things, both there, but also here at the bottom right side, you see the plasticpollution.org website. So if you're interested also in the history, but also a bit of the chemistry behind this materials, these 2 websites are a very good source. So what are plastics in general? When we talk about plastics, we actually talk about polymers that are then combined with different materials such as a plasticizer, a filler, a stiffening agent, or an expanding agent, where then we add colors and pigments to then create different types of plastics. Plasticizers actually allows us to create more flexibility. A filler helps us to avoid shrinkage. Stiffening agents actually reinforce and really give structure to our materials. And expanding agents create foam, so everything towards rubbers and very air-filled materials. And these building blocks are actually very important, because whatever we're using for these materials, they can be extremely chemical and toxic or not. So this is how we're actually going to approach the construction also of the bioplastics. So here you also have a small overview of actually how do we process plastics in many different ways, because I hope this also serves you as an inspiration to have a deeper look on how we work with plastics, which are one of the main reasons of which we like them. And also what are all of those processes actually to refine them, finish them, bring them together. So we do this by assembly. So we use machines to piece and assemble them, and mostly it's done with high density or thick plastic materials. We do a lot of bonding, so glue by polymerization. We can sew them together when we work with very thin layers, so we're stitching them. Oh, I see there is a typo, apologies. But they also work a lot on their finishes, which are fundamental in plastics. So depending on how we cast them or we machine them, we can actually completely change them. Cutting them, of course, manual or by machines, machining them themselves, so by milling, by drilling and turning them, thermoforming, so heat shaping them, calendaring, which is very similar, but then using calendars and impressing 3D patterns on them, casting all of these materials many different ways, extruding them through 3D printing, so a digital extrusion, or by injection. And there are actually quite some more different types of processes that we could list here, but these are some of the main ones used in the industry. So now an introduction on actually bioplastics. So how can we take all of this knowledge about plastics that we have built in the last couple of 100 years and actually turn this into resources for bioplastics that are both bio-based and biodegradable, if not even biocompostable. So all of the materials that we will look at today in this list are actually biocompostable. We'll look a little bit at gelatin plastics, AGAR, alginate plastics, quick mention on casein plastics, even though it's something that I prefer we do not do in labs since we need formal data to process those, and that is actually proven to be carcinogenic. Also some cellulose plastics, chitin, or ketosand plastics, and some starch-based plastics. So how do we craft bioplastics? As we were saying earlier, we have this sort of like building blocks to create different options. So our polymers can actually just be the agar, the alginate, the gelatin, the starch, and all of the other materials that we saw earlier. For plasticizer, most of the time we can just use glycerin. Fillers can be, for example, eggshells, chalk, but also fibers and oils, different substances that avoid the shrinkage and actually keep the volume of our bioplastics. Fibers or actually natural debris, leftover foods, while for expanding materials we can use green soaps and green emulsifiers. As colors we can use natural inks and pigments that we learned how to use in the biochromes class. This is a quick list of researchers that are actually mentioned in the specific section, and I'll present some of their work and actually why I really enjoyed the way they've been researching across these different types of bioplastics. So see this also as a huge inspiration session and learn from each other and from all of these amazing people. So we will start with an overview on agar and alginate bioplastics. So agar is a jelly-like substance obtained from red algae, and it's a polysaccharide, and we use this mixed with water, glycerin, and agar-agar powder, which is very often found also in grocery shops, Chinese shops, because it's been used for hundreds of years for actually culinary uses. But it's a great material to create very thin films, very flexible, never stretchy, but they really resemble thin sheets or foils of plastic. On the left side here, you will see this kind of schemes coming back and forth within the presentation. So on the left side, you always find a sort of how-to, what are the big steps of creating an agar bioplastics, what are the raw ingredients needed for this, a short list of tools, but also what is their water resistance and heat resistance. These are not extremely precise because those depend very much also by the thickness with which we cast, by the material itself, the raw material, but also the conditions in which we work. Meaning that actually room temperature in Amsterdam might be very different than room temperature in Mexico right now, for example. So all of these conditions are quite different. But you have a vague indication that helps you. And actually within your documentation, I really hope that you also start working towards understanding and analyzing the materials. So you're expected to craft them, understand them, but also analyze them a bit so that you can understand what are the pros and the cons of each material. Where usually in regular plastics, we think that the pro and the cons are the same thing because we say, yeah, it lasts forever. It's beautiful because it's waterproof and it lasts forever. But actually that is also its main issue. It's in no way biocompostable or biodegradable. While for a material like agar, agar is a little, bioplastics made out of agar, for example, a little bit more heat resisting than gelatin bioplastics. So they melt at around 85 degrees, but they are in no way water resistant. After a couple of hours, they start dissolving again. Well, we will see that also alginate bioplastics are much stronger in this direction. These are some of the recipes, so feel free to use these. These are a mix of different recipes that we have crafted, starting from also all of the recipes that are out there in the world. And none of these are an invention. I hope not to hear anybody saying, I have invented this material, because what we actually do all together is creating this huge library of recipes, and they all work slightly different depending on where we're located. On the other hand, all of these materials actually come from heritage techniques. These are all things that since prehistorical times we have been using. We had only biodegradable and biocompostable materials until we created synthetic plastics. So 90% of things have been tested before, but we need to re-understand and re-evaluate them and actually start using them for our productions. But please document whatever variation you create on all of your recipes, of your local recipes, others that you find online, or if you use these, whatever you use, credit who is making them and the adjustments you have created. These are actually some of those recipes described. So you have like a step-by-step in detail, but also what are the materials and a little bit of the properties. So they're categorized as either foil or plastic or solids. When we look at alginate, actually, alginate is extracted from the walls of the brown algae rather than the red ones. The only thing that these two types of algae have in common is the cellulose in them. And the process is a little bit different because when we work with alginate bioplastics, we work with a mix of sodium alginate with glycerol and water, sometimes also adding olive oil, and then a separate substance, which is a calcium chloride hydrate. So it's calcium chloride and water, dissolved in water, that actually acts as a curing agent. This bioplastics is actually waterproof. So it's very interesting in the way it behaves. And the only moment it starts breaking down is when the water has an alkaline pH. So you can compost them and you can biodegrade them completely as long as you have a very alkaline pH. But on regular neutral pH of what you have in tap water, they will not dissolve. So this is a sort of like a good way of seeing something bad about these materials and something good, and actually trying to use what is good in it at our advantage. They are very heat resistant because the sheets that we have casted were fine up to about 150 degrees Celsius. They started drying up a bit and crumbling, but they never melted. So this is quite an interesting material with very interesting properties. And I really hope that you will experiment a lot with it. These are some of the recipes. They all come from different sources. Some are variations that we did here, and actually the bottom one is from a student of last year who did an amazing job in researching this, and her work is also presented further on. These are some of the recipes. So you will have these two. I will upload the corrected ones. I see there is a mistake here. Apologies. And now we will see some examples of both agar and alginate projects. This is quite a famous one. I think many of you have seen this. This is actually a beautiful alginate-based bottle that completely biodegrades by itself. So this one is completely biocompostable by I. Johnson. This is the work of, oh, let me see, apologies. I want to squeeze this out so everybody can see. This is the work of Erik KLARENBEEK and MAARTJE DROS. They are two Dutch researchers and artists that work a lot with biomaterials, and what they actually created here is an algae PLA bioplastics, where they use algae as a filler for PLA, and this contributes to these beautiful colors, textures that they were actually able to 3D print. They also were in the Dutch Design Award last year, and their work has been showcased worldwide. The materials feels beautiful, which is quite a pro. Her name I always have a very hard time pronouncing it, so I hope I say it right. AUSTEJA PLATUKYTE. But she makes beautiful materials. Her work comes back 3 times in this presentation, so I really would suggest you also to have a peek at her work, because I find her work extremely well refined for being very simple agar bowls. It's incredibly fine, the detail with which these are casted, and she's managed to actually have them also waterproof, so to contain materials, food, sorry. So you can see also the little bowls on the side. They are not only incredibly pretty, but also extremely functional, and they're fully compostable. AMAM is a research studio that actually created all different solutions for packaging, because this is where we see a lot of our plastics, flexible and non-used every day in supermarkets, in shops. 90% of plastics are in those packaging parts. So they were really looking at how can we foam them up, but also cast them into very thin sheets to resemble all of these materials that we see in the shop every day. And these are all based on agar. Margarita FOLLERT created a whole series of different things with ALGINATE. So these are different straws, packagings, and very cute, beautiful different types of colors, all natural. CAROLYN RAFF creates beautiful beads. So these are all, these ones are all agar. So these are casted, cut, and then used as embroidery. So we also don't look at it as just packaging or big materials, but also something that you can turn into something very fashionable or small accessories. This is a lot more of her work, also really working with textures or actually creating, as you see in these ones that are all dotted, smaller and thicker textures, and then combining those. And also here you see that actually the range of materials and colors is nearly infinite. And you can, of course, laser engrave them, laser cut them, or use mechanical tools to chop them up. Either way, they are extremely pliable and they look and work very similarly to plastics. This is the work of JASMINE LININGTON, where again she's using them almost as beads, where they've been cut in very small, beautiful samples, all slightly different, and she's creating this alginate sequins, which are then therefore waterproof, but of course, as with some soap, I wouldn't put this in a washing machine, I think, because some soaps and other cleaning agents for washing machines can be alkaline, which means they will melt again, unfortunately. But if you think of it as a couture piece where it doesn't have to go in a washing machine, sorry, then these are perfect embellishments. This is the work of one of the students of last year, where actually Stephanie SANTOS really worked on creating composites and materials where she uses different types of bioplastics. These are both agar and gold leaf to actually create a layered material and then laser cutting this. And she was also using this instead of stitching certain parts, so almost like a glue to actually bring parts together. So you have the belt, and on the right side, which also has gold leaf, and the laser cutted top on the left side, while the kimono under has been glued together with different types of bioplastics. This is the work of Catherine. Catherine created this beautiful leather look like alginate top, and then actually covered it also with mica powder to create this beautiful shimmering, and it's of course been laser cut. What you also see here is how clearly it's perfectly laser cuttable. Gelatin is another material that we use for bioplastics. So it is less water resistant and it's definitely not heat resistant. On the other hand, this makes it a material which is really pliable and which you can keep using. Think about making something in gelatin, being unsatisfied with it, and then actually remelting it again and cast it again. This is a material that just needs a little bit of extra water and a little bit of heat for you to be able to use it forever. So you can keep adding a little bit of water and a little bit of gelatin, and you have a new material. Makes it also quite good for mold making. The only thing you need to think about is that it will shrink as much as the other two. These are some of the recipes. Again, with gelatin, it's really easy to actually create a very vast range of different types of materials. So we work on both resins, plastics, silicons, and foams. And actually here you have the same, but then with some pictures, so you can really also understand what I mean. The sample on the right side, the bubbles are completely stuck within the plastic, and it really acts like a resin. We're standing onto a little cube made by the same mixture, and it just doesn't break. The only thing it's sensitive to, it's heat. The foams actually really bounce back with gelatin, and the silicons become incredibly stretchy. This is one of the most stretchy bioplastics. So it fully stretches in every direction, and it feels and looks like a silicone, which is not something so easy to create with bioplastics that are also biocompostable. And all of these, again, are biocompostable. That means that you could just throw them out in a canal in Amsterdam or in a park or in your garden, and they will actually start decomposing quite fast. And here we will look at some of the gelatin projects. So MIRIAM RIBUL has a beautiful booklet on issues, so you have the link down there. You can have a peek. There is a lot of recipes and information, and she's using it in many different ways. So by sort of extruding it into very thin layers or into strips, but also using it as a sort of glue between different materials and creating harder materials with those. Juliette Pepin created a very interesting analysis also on her work. So for the ones of you that are determined to actually understand your materials in depth, she has created quite a detailed understanding of her materials, where she really analyzes them for moisture, for smell, strength, flexibility, and so on. And then this actually allows her to create a very clear description and comparison between all of the different materials. Some of them are colored, and some of them she didn't use any coloring agents, so that you also can compare what does the pigment do to your material. This is an example that I always find personally quite fascinating, because these are insect shells from Coleoptera mixed with bioplastics. So this is a waste material that's not been used and then actually reassembled into quite a beautiful and textured material. Because imagine, I would say, a lamp made with this would create beautiful reflections and actually very different patterns. This is the work of MAYAN PESACH, where she uses different types of food waste mixed with gelatin to create different textures, but also colors. What's mostly striking for me here are the beauty also in the colors, and this is very easily extracted also from the class that we had 2 weeks ago on the biochromes. So explore further on those combinations. This is some of our work. So this is actually a quick capture of part of our material archive, many of the different samples. All of these are gelatin samples, some of them on fabrics, some of them casted into fabrics, on the right side, you see foams, rubbers. There's many different types that we could try to imitate other materials. Here you see some more of them. This one is one of my favorites because this is actually a sort of like gradient in materials, where on the left side we have bioplastic silicone and on the right side the resin. And what we did here with Maria, who was researching here with us for 3 months, is actually trying to create all different types of gradients to understand how the material, the same exact quantity of the material reacts and what happens in the middle, in the mixed section, where there is 50-50 of both materials. This is a bioplastics that we crafted also with the extract color from the Iantinobacterium lividum bacteria. So you can also use the bacterial pigments to actually color your bioplastics to create a fully bio-based and compostable material. And these are 2 experiments on a mixture of fish scale plastics and gelatin, where the mixture of these 2 actually binds really well together. The glue coming out of the fish scales and bones binds very well with the gelatin, and these materials are actually rock solid. They're really hard, really durable, and they're quite hard to break. This is some of the works from Fab Textiles with the beautiful bags of Clara, which also show you how easily gelatin again is laser cutted. She made all these beautiful files for these bags to then be actually assembled with modular systems. So there is no stitching involved. And a lot of their recipes, we will present 3 different booklets. This is one of them. And then the other ones are presented in the other sections. And this is the work of last year from Greta Alessandro, who actually used many different biomaterials techniques, because this dress is actually a little bit of kombucha, a little bit of bioplastics, and some of the latex. And what her concept was actually to create a dress that changes over time. It means that you have a body under, and then a 3/4 skirt, so sort of like a long top, and then a skirt part under. And based on actually the lifespan of each material, she has designed the dress. Means that the bottom part will fade first, then you will still have the top, the second layer and the top, and then at the end of the process you will be left with only this bodysuit under, just made out of latex. And what this was a little bit all of the overview on bioplastics. So I wonder if there are any questions, because otherwise I'll continue with the leathers. So we're going in the next section, we're actually looking at materials that are in no way leather, but somehow resemble leather. Are there any questions?
Yes, I have some question, because I try how you avoid to have molds when you dry your preparation. Because I try with coffee ground, I try with gelatin, and I have plenty of molds on it.
So it depends a lot by the both by your environment, so the amount of moisture actually in the air, because that really contributes to the formation of molds. For example, here in Amsterdam, I have never had mold in any of the bioplastics, but that's also simply because this room has its separate heating system, which actually makes the room quite dry. So that contributes a lot, but also the amount of water within the mix of your bioplastics. So you will see in the recipes, some mixes have actually way less water in them. That makes them a little bit more difficult to cast. But also there is less chance that they will dry faster, so there is less chance for mold creation.
Okay, and another question, because I try many recipes. So first, I get rid of all the one with like cup or spoon, or because it's not really precise. And I tried plenty of them, but the problem is when is a good time to stop boiling it? How you detect the good time? Because I had plenty of try and it was not working very well.
So what I've done in the last year is actually only working with induction stove, because then I can sort of monitor the degrees much better than low, medium, and high heat. So
Okay.
it goes, the ones that we have now going for 20 and 20 degrees. And that mixed with the specific amount of time and the room temperature, actually you get to a quite precise recipe. But still, if you will have to fill in all of the variables to actually have a precise recipe, then we end up into some biotechnical protocol of like 40 pages.
Okay.
But it really comes with sort of, it's like cooking.
Yeah, it's like
It really
cooking.
comes
Yeah.
a lot with
Sometimes
experience.
it become white, so you know that you are not so far, but it's really
Yeah,
hard
yeah.
to have the good time. Okay.
Yeah,
Okay.
totally. And also trying to use what I experienced, trying to use the same tools. Somehow
Okay.
that allows me to actually feel the material better. So always try to use a similar spoon and the same pan. Somehow it helps, at least personally to me.
Okay.
To always try to create the same environment. If there are no other questions.
2 questions more. There are
Yeah.
questions on the chat.
Yeah.
One question is,
I see.
which one is stronger? Okay, cool. Yeah.
So it depends in which way. In the sense that agar based, it's stronger against heat, but it still melts in water within it starts melting in water within a couple of hours. Gelatin is very heat sensitive, so already at 50 degrees, it really starts liquefying. And if you put it into a microwave, it's like 10 seconds and you just have soup again. But alginate bioplastics, being waterproof in that sense, you can create a quite thicker material. They shrink a lot, so you might need to use some fillers, but they're actually quite durable. So the only thing they don't like is very alkaline, or not very, alkaline water, alkaline environment, because they will start decomposing very fast in alkaline environments. Powered by plastic to heat, okay. All of these are also in the boxes of the recipes that you will have in the slides this evening. You can find actually all of these answers. Yeah. And food waste, there will be after also a little section on food waste, and also in one of the booklets is on food waste, made from Anastasia. So we can look at that later on. It's already 5, and I'm not even halfway. I will continue.
Okay. So one quick comment for Jean-Marie, because here we had issues with molding on the bioplastics, and the way that we actually fix that is that when we cast on the flat surface, then we leave the surface drying in an angle, not horizontally, so the water excess will just drain out.
If it's thin enough. Yeah. Okay. So this next section actually focuses on leather lookalike materials that have nothing to do with leather. So these are some of, here you have like a quick list of different types of them. So we will look at microbial leather, fish leather, fruit leather and food waste, algae leather, tempeh, fungi, lab-grown leather. And then there are many examples also on coconut and pineapple, which for sakes of time, I actually cut out. So microbial leather. When we talk about microbial leather, we actually talk about kombucha, a drink that is spread worldwide since forever. And what is it? So it's a SCOBY, so it's a symbiotic colony of bacteria and yeast, where the bacteria feeds on the sugars and on the tea, and then is able to create a very acidic environment and spin layers of cellulose. And then these layers of cellulose can be dried up, after treated with different techniques and different recipes, We actually have a couple of different recipes coming from different people, and they create a material which is somewhere between leather and paper. It can still be very soft and very pliable, depending on how you after treat it, or it can become very dry and brittle, almost like paper. Especially looks a little bit like oven paper sometimes, so like parchment. And a very funny fact is that 2 years ago, they did a worldwide mapping of different strains of kombucha, and just a few people participated, and then they actually said that they found at least 150 different strains of kombucha. Because being bacteria, actually, it evolved in many different ways, and all of these are quite different. So the kombucha that I have here is definitely not the same kombucha that any of you has somewhere else. Unless I have give you a piece of mine, then you might have the exact same. But be aware that they all behave the same, but slightly different ways. So they might like something more or less, or they might absorb color more or less. This is actually just a quick zoom in on the kombucha bacteria under the microscope, and what you actually see here is all of the bacterial cells, and on the right side of the left image you actually see this SCOBY, so this pellicule of, I see the picture from Jean-Marie, sorry. Yes, I see you very well prepared. But actually, so these layers that you also see in the picture of Jean-Marie are the actual kombucha SCOBY, so which is what we cut up and share, and when we have exchange parties for kombucha, to actually try and grow all different types. So this is both your starting material, but it's also your final material before being dried up. So here you have a very simple recipe and steps on how to do this. All you need is actually tea, sugar. Some people add a little bit of vinegar, but that depends very much also by the strain they have. The one that I have here, I never add vinegar because it turns everything into acidic very fast by itself, because bacteria most of the time do prefer acidic environments. But many other types really need this. So I would say test both ways. And on the other hand, I also added another recipe and also a very interesting after treatment that you can find here. So also you have their website and their contact details, but they also have a lot of information on Wikifactory. So I would say have a peek, especially at the after treatment, because the kombucha that they showcased this summer at the Fab 15 exhibition was extremely beautiful, soft and pliable, and not sticky or not brittle in any way. So this is actually quite a good after treatment for the material that I would suggest. In the past, we have tried with all different types of beeswax, almond oil, coconut oil. Everybody has different recipes, but I truly believe that this one actually turned out to be quite amazing. And this is how they used it together with Surzana Radneva. She's actually the fashion designer, and they were the material designers, and they created this beautiful kimono that you might have seen also left and right online. And it was for the ones in Barcelona or going to Reshape tomorrow, it was actually a winner also of last year's Reshape. And it's quite a beautiful kimono, an incredible material. And this is the work of Suzanne Lee. Suzanne Lee is actually the master on kombucha and microbial leather. She's been the one showcasing this for the last 15, 20 years worldwide in all different types of projects, and also the co-founder of Biofabricate. And this specific example is, for me, her most beautiful, because here you actually see all of the properties of kombucha. You see how you can dry it in a full 3D shape and how it will maintain it. Of course, the issue with kombucha is that it is sensitive to humidity and water, meaning that it will start swelling again if it's in contact with water. These are two of her jackets. What I very much enjoy of the work of Susan Lee is that it actually always brings us back to real objects and real clothing and accessories. So the left side, you have a kombucha bomber, which has been stamped with natural inks. And on the right side, it's a kombucha jeans jacket dyed in indigo. And if you look at these two, you really, especially for me, the indigo dyed jacket, it feels like a jacket that could be in a shop right now. It's incredibly beautiful and detailed. And actually, this really brings across the message of working with alternative material. This is some more of her work, also with laser cutting. Kombucha laser cuts beautifully. And these are also a pair of shoes made, coated in kombucha, inside out, everywhere. And for the rest, following very traditional shoemaking technique. But also what you see is that the kombucha being so flexible and being able to dry itself and stretch into 3 dimensions before drying, you can create a perfect shoe fit in one go. This is a video of actually a Japanese artist who has been working on digital fabrication techniques mixed with kombucha. If you're having issues in visualizing it, there is the YouTube link also at the bottom. So what we actually, well, so what he did is actually created a jacket in fabric, 3D scanned this, and then created the molds to grow the kombucha already in 3 dimensions. So you CNC'd all of these molds. Here you have the 3D piece on which he's actually going to grow the kombucha. And then, of course, drying it on top of those molds, that really helps you to create this 3-dimensional effect again. So both growing it, but then drying it also on the same shape. And because it is such a flexible material, you can easily stitch it under a sewing machine. It can also very easily be dyed with either natural dyes while growing it, with beets or hibiscus. Everything that is acidic actually works really well with kombucha, so you will get a lot of pinks and reds, and not with the alkaline ones. But what you can actually do is extract the pigments and then use those after, just before drying and just before pre-treating it, so that you can create very colorful materials as well. This is the work of Moya Hoke, who actually created, I think, one of the largest, most complex kombucha pieces. I've seen people growing bigger ones in squares, but never into a shape. So she hand welded this mold, this growing tray, already in the shape of a suit, so that she didn't have to waste any material and she didn't have to cut anything. So what you see is that actually the big hole is where your head goes, then the parts flap down around your arms, and your pants are stitched into the back. So you have a one-man suit, all made out of kombucha. She can tell you about how smelly this was, because the problem with kombucha, especially in large quantities when you can't really cover it well, is that it smells a little bit like honey and vinegar mixed. So it's quite a strong smell, which is produced by the bacteria while they're spinning cellulose and creating a very acidic environment. So, but when you grow very big pieces, such as this, be careful of where you grow it, because you will have the smell accompanying you for the next couple of weeks. Another very important thing to think about is actually the general temperature with which kombucha grows, which is between 25 and 30 degrees at its best. Meaning that if you have a stable 30 degrees, it might grow within a week. But when you work at lower temperatures, such as us here in Amsterdam, for example, it might take up to 1 or 2 months. So it will keep growing, but it will just go a little bit slower. What you can do is, of course, put it next to a heater, or grow it in bain-marie with heated water around it.
I have one question. The mold seems to be in metal, and normally the metal is not good for kombucha. How it
It's
works?
coated.
Ah, okay.
This is the work of Sami Jobbins, where actually what she does is created laser-cutted structures and then spun the kombucha above it as a sort of film. Because of its elasticity, it actually creates super smooth surface, but really keeps in all of the textures. These are some very funky wallets. I quite enjoy them, both for their transparency. So they're really using the transparency of the material so that you can also see within your wallet instead of the plastic. But also because it really does feel and look like leather when you treat it well. So it can become something very useful. Of course, when you stitch it with a sewing machine, what happens is that you perforate the kombucha. That means that water and humidity can actually penetrate really well. And it will start swelling again. So it might not be the ideal solution, but we're getting closer to it. This is the work of Emma van der Leest. Emma van der Leest is actually famous for 100 different things, but this is one of the works that I do really enjoy when she was still working for Biocouture London at Suzanne Lee. And this is a beautiful little bag that she has both laser cut, laser engraved, and while the kombucha was drying, she's used different types of pigments in powder to actually color the surface. This is Emma Sicher, who created mostly packaging. So if you Google her work, you'll find very clean-looking packaging like this. I love the picture of this little sugar bag because this is something that we use constantly and everywhere. And we have plenty of this kind of small bags for our foods. And this could very well be done with kombucha. And this is a project of one of the students of last year, where actually what she did was not crafting a project or a product out of the kombucha itself, but she created an electrospinning machine, which she called kombucha, where she's electrospinning cellulose from kombucha. So instead of growing it in layers, she was electrospinning it. So the whole machine and how it functions is on her documentation page of last year. So you can look for her name in the class archives. Fish skin. So fish skin leather is nothing new, actually. I find it always very funny when it comes up into research or exhibition as like the innovation, because it's nothing new. It's something that we've been using for centuries. I've been working with this forever. Here you have, for the ones of you that want to test this, you also have a little how-to and what are your ingredients. It is extremely simple to create a translucent version of a fish skin leather, where we use glycerin and ethanol 50-50, and actually continuous movement of shaking. So you could put everything in a bottle and then shake the bottle for a couple of minutes every hour. And within a day or two, you have skin that has been tanned. So these are actually some of the Inuits examples that I was mentioning earlier. So when people say this is a new technique, I'm like, no way. This is hundreds of years of experience built up and working with the materials in our environment. So whatever is abundant locally, have a look at that and see how you can utilize that. Also learning from the other recipes. Maria Hayes actually created some very beautiful bags out of this, but there is hundreds of different examples out there. So this is carp leather, which is widely used in the industry. The thing is, this one is naturally tanned. And most of the leather is usually tanned with chemicals. So, and those chemicals are extremely polluting. Well, if we do it naturally, which is simply how we used to do it a couple of 100 years ago, we can tan with different types of barks or nuts, or for example, even tea contains tannins, very low, but it contains tannins. Or for example, with tara pulver that we were using last time.
So anything that contains tannins, that's the thing.
Yeah, you need quite a high quantity of them. Yeah. And this is a stool. I always show this, especially because it is important to mention that salmon skin and other fish skin leathers are extremely durable materials, extremely strong. Very heavy person can sit on this stool, and the joke is actually that the stool might break before the leather, because this leather is extremely strong. The way this material builds up on itself, the way the skin constructs itself, actually creates a very strong material. And here you can see some more details from above. This is still Nienke Hoogvliet, where she actually used laser cutted little parts of this and used them as sequins. And this is a little bit of a special thing. This is jellyfish leather, and I find these, they're basically dried in shape, and I find this bag absolutely stunning. The material is beautiful, and this is actually done with jellyfishes that were washed, yeah, ashore, yeah. So it's also, you never know what is abundant around you or what accidentally is abundant in that moment because of another catastrophe around you or whatever else. So take advantage of those moments and don't actually just go and look for something that is not local or not easily found, because that will make absolutely no sense. So mycelium and mycelium leather. So we will look at a few examples. Here you have both a recipe for a vegan leather, so a very soft, very thin material, and the thickness actually just depends on how much you let it grow or how many substrates do you layer on top of each other, and the other one is a simple recipe for a composite. So this is the work of Maurizio Montalti when he is in his, let's say, artist side at Officina Corpuscoli, which is a studio here in Amsterdam that he's founded. And this is his experiments on working with mycelium leather. So this is high pressurized mycelium leather, and also some experiments in shoemaking. But what he also does is he started a company called Mogu in Italy, where he actually scaled all of this up and tried to understand how he can create also insulation materials or building materials that are bio-based and biodegradable. This is the work of Aniela Hoytink, who actually made a dress out of growing mycelium into small petri dishes, and then patched these over a mannequin to create a one piece. So there is no seams in here. This is a material that you can order in small quantities from Grado Zero. It's called muskin, and it feels amazing. If you have the chance to purchase some or to see some at the material archive, please do, because it feels like sweat. It looks like a thick, beautiful sweat. It's soft, it's hairy, it smells good, it has it all. It's quite an incredible material, and it comes in 3 different sizes that you can purchase also online, so small samples. And this is MycoWorks, where they also have been working on all different types of leather and how they can actually texturize this to even feel more like leather. But what I enjoy the most is actually their resource page. So you find a lot of other information also on their website. You have this one, but actually I believe they have a better and updated version of their resources. So go on their website and have a peek, I would say, if you're interested in working with mycelium. Fruit leathers and similars. So here we also really look at food waste. This is a project that started many years ago here in the Netherlands, in Rotterdam. It's called Fruit Leather, where actually students went to the market to see all the trash that had been disposed during the market. And the funny fact is, the same way for fish, we actually pay for our trash. So all of those leftovers, instead of being trashed and the market owners that had to pay for it, you could reuse them and create new materials out of them. This way we create a full loop for material in all of its shapes. Because somehow some stuff doesn't get sold, but it doesn't need to mean that it goes straight into the trash. We can actually use it to make beautiful things. And these are some of their samples. They have a lot more also on their website. And this was a concept bag. And some more. This is the work also of Anastasia at Fab Textiles with her Inter Aurore, where they created a beautiful coffee waste bag. And a lot more information also on the booklet with another intern for the food waste bioplastics. So these you can find on Issue and you can have a look there. Okay, so we've been talking a lot about algae as alginate and as agar, but we have actually not looked at using algae by itself without turning them into powder and then reutilizing them. This is the work of one of the most amazing researchers ever. I mean, Violaine is not one of the most famous people working on algae and algae leather, but I do believe that she has the most extensive research in this direction and the most beautiful samples. This, for example, is a fabric made out of layering little strips of seaweed that have been cut into shape, and it feels and looks incredible. She's also woven it a lot, cut into strips and then woven it into fabrics. And we had all of her materials, samples of her materials showcased 2 years ago in Paris for a beautiful exhibition about biomaterials. And by far, I think this was one of the most interesting samples that we had there, because nobody could guess this was made out of different types of algae. But also Gerard Veenhoven, another Dutch researcher, who actually looked at it from a very different point of view. He actually found out that there was a huge issue on the algae covering the sea in China and not letting the light through. So what happens is that the chemicals in the sea actually create an overgrowth of algae, and these don't let any light through into the water. That means that the whole sea life is dying. So he approached it from a logics point of view. We need to get rid of this algae. Let's make something great out of it. So he's been working for the last couple of years on actually creating different types of fibers out of it and materials. Julia Lohmann uses it as a leather stretch sort of architecture almost material. So basically what she does is she stretches it out onto large constructions into many different ways, also creating beautiful masks. And for each of these, so she's using different types of giant algae. So she's actually treating them as if it was a leather rather than really decomposing them, extracting what she needs, and then working with it. So these are spun and flexible, but very smooth. And this is the work of Nina Edwards Anker, which is actually similar but sort of slightly different, because she allows them the chlorophyta. So this is a different type of algae than the ones we saw before, but she allows them also really to dry into shape. So into different types of crunched up textures, and uses really also the fact that these algae are translucent. And you can actually find a lot of her work on Studio Nea, which is her studio. These are some high-tech lab-grown materials. So it's a slightly different approach, where we actually look at lab-grown skin. This is one of my favorite projects because it really uses growing skin in vitro as a new material. It takes forever, and it's probably the most expensive material ever, but it's quite incredible because it looks and feels like leather. It is actually leather, and she created extremely beautiful samples and also texturized each one of those. And real garments, which is not something that happens that often. Modern Meadow, that has been working forever on actually creating, again, in vitro grown materials, which are slowly getting there because everybody's saying, I have never touched one of the samples yet, but everybody says they're actually quite amazing. So still curious to see how that is going. No idea. Well, the work of Elisa Brunato, which works with cellulose extraction in sequins. She also presented now at Dutch Design Week, last week and the week before. And what she does is uses the crystallization of cellulose to actually create sort of like reflective material where the cellulose sort of aggregates into crystals and uses this light refractancy to create sequins. So not using plastic-based ones anymore, but actually really working on bio-based materials also in this direction. Some variations on silks. And this is a beautiful piece, V&A, and it's a piece designed with hundreds of different spiders from Madagascar, where the silk, let's say, spun by the spider has been collected and then traditionally spinned into fibers and into yarn, and then this yarn has been woven and then embroidered on top of. So this whole cape is made out of spider silk, which is one-off piece, and you will never see anything like this anywhere else. On a completely different point of view, actually, this is the spider silk Adidas. So it's industrially engineered spider silk. So it's not natural in the sense that it's not collected by spiders like we had here. This is really engineered. And a variation on that is also the work from Both Threads, which started with a really funny also product with where these pink ties made out of spider silk. And this is also industrially engineered spider silk. So they actually try to understand how the spider silk, what are the properties, how does it work, and how they can reproduce this industrially. This is a slightly different section of what we call cooperation with nature, where we actually really collaborate with nature from a different point of view. While nature is growing, we sort of work with it. There's, of course, the work of Carolyn. And if we do have the time, also let me see. Yes, I think we have the time for that. We can check out also a small video that comes with her work. Let me see if I can exit this part. This is, for me, always a beautiful video of her work. There we go. Can you still see my screen? Do you see the Vimeo?
Blue.
No. It's because I shared only the Vimeo. Sorry, guys. So I'll share the Safari. Okay. Full screen. And again, if you, for any reason, can't see the video, you can use the link that is at the bottom of the slide.
Welcome to the Hydroponic Biofactory, England, in the year 2047. You're entering a large-scale high-tech. Plants have been reprogrammed and engineered to become multitasking. By the year 2050, we'll face several critical challenges. World population is predicted to reach 9 billion people. Producing enough food and textiles, amongst other things, will be a challenge unless we update our agricultural and manufacturing. Here, we grow hyper-specified plants that produce fruits or vegetables at the same time as fabrics. This is not just fiction, but an illustration of what will become possible if the promises of synthetic biology are fully delivered. Hydroponic biofactories could become the new sustainable manufacturing of the future. Synthetic biology is a new science field which is turning biology into control of DNA and its manipulation enables us to food the living like we write a software. For the first time in human history, we are able to design and engineer new synthetic plants, grow and harvest custom-made materials. Of course, there are ethical implications to consider. This technology can self-replicate, but can we really control it? And what becomes of the designer in a future where everything is reduced to programmable coding, even the living?
So I hope you could see it, and otherwise, again, the link is also there. I'll start sharing again. Here we go. So at the bottom of these slides where there is a video, you can always go back into the video. And then the work of Diana Scherer, who actually did what everybody said was basically impossible. She really grows the root already into a pattern, and she really domesticated them into incredible definition. So you also see here how detailed those are. She grows from extremely huge to extremely small samples, and they're all very detailed. She's also able to create different structures within different parts, so much thicker or open, and she's made a beautiful dress this year. She was presenting at the Dutch Design Week as well. And here's some more of her large fabrics. And here we have a short introduction on some mixed media materials, which I very much enjoy. So it's a weird collection of all different work that doesn't fit really anywhere in these categories, but should fit everywhere. So this is the work of Tamara Riola, if I'm saying it right, who's actually been working on tree waste. What is tree waste? Tree waste is pine tree fibers, because those little spikes are actually, she's able to basically spin them again into a sort of yarn. So she softens them and then spins them into a yarn, and then creates different types of materials, either by sort of felting it or by really creating yarn. And these are all done with what we call then pine tree waste, because they shed anyway. So why not using it? And this is the work of Samita Polakova, who creates the most interesting bark fibers. So actually she's from, if I remember correctly, she's from Lithuania. Yeah. And when she showed me this piece for the first time, I met her at on a workshop of somebody else, and the material is quite incredibly soft. And this is a traditional technique that they use there, where when cutting the wood, they take the bark off, and the layer between the bark and the actual wood is what she uses. It's this very fine lining that can then be cut into strips or not. As you see, the big roll on the right side is not cut into strips. So here you really skin the bark tree in one go, which is quite difficult. But you can also, since it's so soft and pliable, when it's drying, you can also weave with it, or you can knit with it, as you see with her gloves. But also the patterns and the natural textures of this material in the woven and the knitted pieces, everybody always thinks it's leather. And it's bark tree. This is the work of Billy van Katwijk, that actually uses stomach cows and tan those to create new leather pieces. To be honest, we eat this in Italy. So somewhere it's not really waste. We love this as food. It's really tasty. So somehow when I show this to my dad, he's like, this is not waste. Are you kidding me? We eat this stuff. But it's amazing material. Actually, the different parts of the cow stomach have completely different textures. Some of them have this very cute little tentacles that you see a little bit on the left side, but they are so beautiful on these bags because you can really see them, how they move and actually how they pass through the stomach. but also these larger pockets on the right side image, when tanned, they become beautifully dark brown leather, and the textures are something that we could not create in any other way. So again, don't look at any animal like they have any waste, because they don't. Either eat it or turn it into a beautiful biomaterial. Or don't eat animals at all. So use everything or nothing, I would say. At least this is my personal view on all these materials. And this is again the work of this amazing artist that I cannot pronounce the name of, who here instead has been working with pine tree resin composites, creating beautifully smooth resins, really hard materials. And you see also on the left side again her bowls made out of agar, actually, which she uses only for the presentation. But this is all coming from actually heritage techniques from different countries and mixed media, because if we look at pine tree resin, it's been used worldwide, everywhere, in many different ways. If you look at Japan, they make beautiful lacquer out of it. I can't come up with a name right now. Anyway, I will send it around when it comes up. Out of pine tree resin, they make lacquer with which they lacquer everything. Bowls, spoons, even floors, if you're very rich. And then sand it down. And the beautiful thing of this material is that you can sand it down very thinly. And these were some of the experiments. I'm sorry I didn't have a better picture. She has better pictures and better examples of her materials. These were some of the first experiments of Lara of last year, Fabricademy, where she also used natural resins mixed with different media to create composites. So also really an invitation to experiment that way, even though this is not fully embedded in this presentation. So explore many different directions, please. Shellworks is the work of 4 different students graduating from the Royal College of Arts, London, where they actually use crab shell extract, which is chitosan, to turn it into plastics. This is not a super easy chemical process, but it does create a beautiful bioplastic, which is fully waterproof. I will check the time again. We do have time, thank God. So these are some of her samples. Actually, what they did here is map out different translucencies, but also patterns, because depending on how they were drying them, the patterns were actually being pressed. This is actually with all of the materials that we've just seen right now, but also different translucencies for different uses. I will stop sharing so that we can have a look also at their video. I'll start sharing again. Are you able to see the video right now?
Yes, only put it louder.
Yeah. So I wouldn't cast like that,
No,
to
I
be
was gonna
honest.
say, yeah.
You cast above the liquid. You do not go everywhere, otherwise you conglomerate a lot of air bubbles. So also here, what I really enjoy is everything together. They not only have been looking at a material, but also what are the machines and the tools that they actually need to work with this material. So all of a sudden you find yourself starting to design a process, but then the machines you have don't fit that process anymore. So you create new machines, new tools, and then everything on sudden starts to change and adapt to your new materials. Also the way you design, the way you think starts to change. And I think this is quite beautifully portrayed with the very funky machines with the beautiful names. And of course, all of their material research. And last but not least, a quick peek on many different material archives, because there are hundreds of different ones on Earth. Some are commercial, some are completely open, some are started by some of us, and they're in continuous growth every day. So this is a very tiny collection of some of them, but explore, 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 because there is so many out there around the world. And go visit them, call them, ask them if you can see the samples. Say, I'm a student, I'm researching, I'm trying to figure something out. Can I come and have a look? So even on the commercial ones, you can give it a try. Just be nice to them, they might let you in either way. So these are some of the ones that were actually started also by some of us. So by Adriana, by Anastasia, by me here in Amsterdam. There are also some other people that we know. Also, for example, Milano has a beautiful material experience lab with a lot of research and a lot of documentation, same as the ones below. And these are a few of the ones, actually, these are all in Europe. Some of them have multiple locations, such as Material Connection. They have multiple locations worldwide. So that one you might find everywhere. I believe the one in the picture is the one in Copenhagen, if I remember well. This, of course, also Matterfat, very close to JAC in Barcelona, and Surface Matter in London, actually focusing more on all different types of also finishes rather than just creating the materials themselves. And then some more. So have a look, because these are just a vague invitation for all of you to go out there and look at different material archives. Actually also Materio is in many different parts of the world to be found, so you might have one close by. And just to end, just a very happy video that I enjoy. This was actually the creation, this is a documentary made by one of the students that was researching here, with which we crafted the logics and the system with which we catalog our materials. and she made a small video. So the joy, again, is not only crafting these materials. I know you will get lost into making amazing samples one after the other, and then the same as with the biochromes, if you want document, you won't remember how to reproduce them. So this is also very clear indication, not suggestion, to document very well your work so that you can get back to it. So your assignment also this week is to really work on crafted materials and grown materials and document in as much detail as possible how you have created this material. Because if you don't do it, you will never be able to reproduce it again. So if needed, stick a GoPro to your forehead and record everything beginning till the end, temperature included. Go around with a thermometer attached to your arm. I don't know, find out a way. So if you're not very good at taking pictures or writing down every single step, just film everything. Then you will be able to actually reconstruct every single step of your explorations and create amazing materials that you can continuously change. And if you make a mistake, there are no mistakes in this class. So whatever the outcomes is of your experiment, of your material, and you think, no, I added too much gelatin and my bioplastic, too much glycerin, and my bioplastic is all mushy. Funnily enough, this is how we created the first silicone gelatin. One of my students put in like 4 times the amount of glycerin, and all of a sudden we had this incredibly stretchy material. We're like, wow, what did you do? She's like, I don't know. I put like 48 grams of glycerin. I'm like, what? 48 grams of glycerin is a lot. But so all of your mistakes are actually a very good start for discovering something new, but also for somebody else to build upon your knowledge, because there might come a moment where you think, oh, this is super brittle, super ugly, super crap. And next week, some students are like, yeah, I was really trying to find something in this direction, and you might have it, and you just didn't document it because you thought it was a mistake. So don't take anything as a mistake, just an unexpected outcome, and document it and build upon that. And have a lot of fun. And now, questions.
Yeah, I have question.
It's also, we had really loud volume from the video.
So it's regarding the shell works. Is it open source what they made or not? Okay.
I always try to present mostly open source work, but if you're interested in the material recipe, yeah, you'll find that. The machines maybe less, but the material recipe you'll find that online. If you research on, we can also send you some links. If you just research on Kitosan and bioplastics or biopolymer Kitosan, you'll find a lot of materials.
And we didn't have any recipe about using the milk, so?
I have a lot of recipes. I just don't really like them.
Yeah,
unfortunately, working with glycerin, you need to use formaldehyde. It's 2 years that I'm looking for an alternative that creates the same bonds with the milk that the formaldehyde does. And yeah, I'm not a chemist, so I haven't found an alternative yet. But if you do want to try it out, I'm happy to send you some recipes. The only problem is that you can't take the last step, which is actually curing the material in the formaldehyde. Or if you do, please be extremely careful, because the fumes of formaldehyde are carcinogenic. And it's just not something good to work with in an open lab with many different people walking around and touching things.
Okay.
So if you do, really precaution. But it's very easy, yeah? I mean, casein bioplastic, it's simply dripping milk into, dripping vinegar into milk. It's like cheese making. This is very moldy. Cook it. Put it in the oven. Molds also... Ooh! And actually another thing that works against certain types of molds for certain materials is actually create an alkaline environment because they don't like it. So they like acidic environments. So if you add a little bit of soda, that tends to kill quite a lot of things.
Okay.
Yeah, exactly. They're still...
It's my desk. It's okay.
Very good move. Please straight away. Okay, I see there was a question from Tasneem. If all of these biofabrics were done since years, why is the industry still not having it as a common, readily available fabric? Oh, they are. They just stopped producing them. 100 years ago, they were using them. They're not using them right now anymore. So actually what we did, it's very similar to what happened with dyes, right? We discovered synthetic dyes and all of a sudden we thought, oh, we have something amazing. We don't need to use all of the natural versions of them anymore. So we started working with the synthetic version only, which caused us a lot of issues. With plastics, you have a link actually on the third or fourth slide, I think, the history of plastics in general. Please read that because actually we'll give you a very different also perception on how we work with plastics and how they completely boomed. Plastics are an incredibly interesting material because we basically engineer them to our wish and we shape them to our wish. So they are, for a designer, they're the perfect material. You can do whatever you want with it. You basically can program it. I want it soft and hard and stretchy and this, and it will happen. So their pliability being so great and you can use them for anything made them become like the most used material ever. But actually nobody looked at the consequences of what it actually means. Nobody started analyzing, okay, they're releasing microplastics, they don't break down. So if you have something made out of plastics, it will last hundreds of years. Why do we have plastic cups at parties and festivals made out of plastic? And even when it's bioplastics, they are not compostable, they're biodegradable. That means that in very specific environments, they are going to biodegrade, but they need very specific rules. Some of them need to be gassed, some need an acidic environment, alkaline. They all have different types of rules behind the way they break down. But it's not just you throw them in your garden, because this is what people think. They think, I can drop this at a festival and it will be composted in a couple of weeks. No. And this is the problem and the discussion also towards when people say, yeah, we have bio-based plastics. Yeah, thank you. Plastics are bio-based. Are they biodegradable? Are they biocompostable? No, of course not. Then what are we talking about? We just loop back in the same issue. So
I have a question.
It's hard. It's a difficult shift. Go ahead.
About the time. We need more than a week. If we started before, no? But normally,
for the
bioplastics.
Yeah, for the bioplastics, so I expect you to have a crafted material. Of course, grown materials, we can't make them happen overnight. We just have to collaborate with those lovely organisms that will help us. So depending on your temperature, I will check on, no, I'm joking. We will check in a couple of weeks about the mycelium and about the kombucha if you're experimenting that direction, of course. But if you have already some kombucha and you can show how you're growing it, that's already a big step. And also mycelium-wise, I mean, mycelium can grow really fast. So some of them grow within a couple of days. You already see all the spawning everywhere. So take a step at a time. I would say start with actually those materials that need to be grown. So you prepare a little perfect environment for them to slowly develop in the next couple of weeks. And then whenever you are ready to process mycelium into sort of leather, we can have a chat again. There is a recipe in there. There is a description, step by step, made by one of colleagues downstairs. So have a look at that. And then if that doesn't help, I can loop you in on some more links and research papers. Any other questions? You're welcome.
Yes, I have a question. Do you have a food waste bioplastic recipe? Because I didn't see anyone.
Yeah, there is some there. For example, from eggshell, you will find many. I have a lot of, I have 2 or 3 on eggshells at different thicknesses. So they're also sieving it at different levels. Some of them actually look more like almost opal. Like very thin eggshell, so it's chalk actually. It's very thin chalk. Chalk and eggshells were used as a filler in plastics in the past. So we are reverse engineering what they used to do to actually find better solutions for tomorrow, which is somewhere a bit crazy. But I can send you definitely those. And one of them is the one that I did not record, because sometimes I also don't record my own experiments, and somehow created an incredible, it feels like linoleum. When you laser engrave it, it works like linoleum. It's super weird. But it's a mixture of the one of the gelatin recipes, I believe the third one, mixed with, or the second one, mixed with very, very, very thin powder of eggshells, for example. On the fruit leather website, you also find some with oranges. And you also find actually, yeah, you will find a lot online on oranges. And I'm thinking...
I would like to have one on coffee ground also.
Nat can help you maybe with that one. Anastasia made a beautiful coffee bag with Aurora.
I wanted to try.
In general, when you work with food waste, you need to have like a process first of drying the material in an oven or like in a dehydrator best. If you are working with like oranges or like eggshells or like bananas, better to boil them before, so, and add a little bit of vinegar so that it becomes like it
mushy
keeps the bacteria. But a little bit of vinegar, and then you dry them. Then you can make the like trim them, cut them, break them.
It's gonna be smelly.
And then sift, if you want to use it for 3D printing, which is basically taking a syringe and extruding it with your, normally not in a 3D printer, but first you need to do this manually by hand with the syringe. Then you need to sift the material so that you have the fine grains. And yes, I will send some coffee recipes.
Yeah, I would like to try with grapes. If you have ones, grapes.
Oh, you will find grapes also online. There is actually, I didn't put that in. I completely forgot. There is a really nice Italian lady in the south of Italy that has been working a lot with grapes. And she's documented everything that she's done, but she works with 3 different recipes, like squashing them down or extracting actually what's in the on the outside. So actually separating the juices and using the juices, but not the, she uses the outside of the grapes for the bioplastics. I want to check what her name is.
Thanks.
Last year also we had some people doing fish leather.
Yeah, fish leather, there are the recipes in there. Because this is something that we've been doing now for 5 years. But it's like, so there's one recipe recorded in there, and it will give you a translucent fish leather or semi-translucent. While if you want to work towards a suede kind of fish skin leather, it is possible, but it's a lot of work. So it has a lot to do with using different oils and actually drying in between and then oiling it and drying it. And while you're oiling it, you really need to break down the skin so that enters the skins. And then by washing it the last time and breaking it again, you will have almost like a furry suede. Are there any other questions? A fluid mycelium? I'm not
Mycelium.
sure. Mycelium. No, it's not fluid. So it's spores. And what you do is you grow them on a liquid broth. You grow them on a liquid agar, and you just put a very small piece, and then it will actually cover the entire dish within a couple of days and grow this very fluffy layer. If Thursday we will work on mycelium here, I can send some pictures actually of what our intern has done. On a very big, large Petri dish, within a couple of days, there was this stick of like very fluffy mycelium. And there is, of course, many different types of myceliums and mycelium spores, different strains. So depending also on what you use, you will have completely different results. I'm personally totally addicted to the I'm calling it the schizophrenic one because it's called Schizophyllum commune. It creates beautiful patterns, but we have definitely decided that it's a completely schizophrenic mycelium because it grows slightly different every time, but it's always beautiful, no matter what you do with it. But there is many different strains. Are there any other questions? Or on the assignment, on the work? On the complete overload of information. If not, I think I will stop recording